I now call to order the Society's 2,506th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. Good evening. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by JoAnne Hewett. First, the Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates, LLC, for their support. Thank you, Mike. And to the sponsors of tonight's lecture, PSW members Erica and Bruce Kane. Thank you. Speaking of sponsors, whilst these lectures are free to you, they are not free to put on. Even though there are no paid staff and all work of staging the lectures is done by volunteers who do not receive any remuneration for their work, there are still many expenses. The use of the facilities here at the Cosmos Club, for the snacks for the social hour, for software services for maintaining the books, the membership database, the mass emails and the reservations, etc., for speaker expenses incurred in coming to speak, and numerous other costs and expenses. The Society would not be able to operate without contributions sufficient to meet all of them. So in addition to thanking tonight's sponsors, I'm especially pleased to announce that the Society again this year has been the grateful recipient of a 2-for-1 matching grant. All donations from November through January, up to a total of $10,000, will be matched 2-to-1 by this donor, who wishes to remain unnamed. If we reach the $10,000 maximum, the donor will match it with a $20,000 donation, bringing a total of $30,000 to the Society. So please, donate now through January 31st, 2025, as much as you can afford. And let's all please thank our generous, anonymous donor. In case you missed it. I'm pleased to note that the following new members have been elected to the Society. Bailey McCarthy Riley, a program analyst at NOAA, interested in analytical chemistry, microfluidics, quantum computing, and spacecraft payload development, who learned of PSW by attending a PSW event. You know, several people have said that, but they didn't tell me how they figured out to come and attend a PSW event. Gomaro Contreras Delgadio, a system engineer in Huntington Park, California, currently doing an internship with Raytheon, interested in communication systems, radar, aerodynamics, and hypersonics research and development, who learned of PSW from watching PSW videos on YouTube. Greg Zacharios, aerospace R&D domain lead with the American Institute of Aeronautics and Astronautics, fondly known as AIAA, interested in strategic science and technology planning and entrepreneurial activities driving tech innovation and growth, who learned of PSW from attending an earlier PSW event as a guest of PSW speaker member Missy Cummings. And tonight's speaker, JoAnne Hewett, who learned of PSW from the invitation to speak here tonight, and whose interests will be clear in some small part from tonight's lecture. Let us all welcome them to membership. If you are interested in membership, you can access a membership application on the PSW website by clicking on the Join button on the home page at the upper right-hand corner. And if you're here in the Powell Auditorium, you can access the application using the QR code on the business cards on the tables at the back of the room. Everyone with a genuine interest in science is welcome to apply and join. All members are entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, aka PSW, and if you choose to purchase and wear the ribbon of the Society. Also, all members are invited to receptions and dinners with the speaker preceding each lecture. If you've not received your signed copy of the bulletin, that is to say, if you're a recent new member, please come see me after the meeting. Recording Secretary Scott Matthews will now present the minutes of the 2505th meeting and the lecture by Jun Yi on the nuclear clock, scaling quantum systems for precision metrology. Scott, the stage is yours.
Thank you, Larry. Good evening, everyone. On November 22nd, 2024, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined the other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2505th meeting of the Society to order at 8:07 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Jason Ekberg titled Ukraine Conflict, Uncrewed, Ubiquitous, Unprecedented Technology Applied to Modern War. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Jun Yi of the University of Colorado, Boulder. His lecture was titled The Nuclear Clock, Quantum Scaling Systems for Precision Metrology. The speaker began by describing atomic clocks, showing an animation of an oscillating electron with a period of 10 to the minus 15 seconds, or 1 femtosecond. He described how this oscillator acts like a, quote, quantum pendulum, and can therefore be used to measure time. He said that both atomic clocks and nuclear clocks require a long coherence time, maintaining their oscillatory state over trillions of cycles. He indicated that a nuclear clock might be capable of maintaining coherence over 10 to the 20 cycles. Yi described what he called, quote, Bohr's certainty principle, which makes the energy associated with a particular atomic or nuclear transition exactly the same, and Bohr's uncertainty principle, which creates quantum noise that is unavoidable. He said that phase-stable lasers are used both to create a superposition of quantum states and to measure the phase evolution of those states. Because these systems inherently include quantum noise, it is necessary to measure very large numbers of quantum objects in order to reduce the noise. He described the way in which quantum entanglement can be used to further decrease this noise. The speaker then discussed the need for laser cooling. He described how Einstein's theory of special relativity implies that variations in velocity cause variations in the passage of time. As a result, an ensemble of atoms, all moving at different speeds, act as an ensemble of clocks, all measuring time at different rates. He then discussed the manipulation of individual atoms using laser beams, so-called optical tweezers, and the creation of ordered arrays of large numbers of atoms. These optical tweezers can, however, distort the energy separation between the quantum states. The speaker explained that careful choice of the trapping laser frequency can distort the ground state and the first excited state in an identical fashion, removing such distortions. These advances, he said, have allowed atomic clocks to measure time with a precision of 1 part in 10 to the 18. He indicated that the complexities associated with atomic clocks motivate or justify the development of nuclear clocks. The electron states of atoms are easily perturbed by a variety of physical parameters, while processes in the nucleus are shielded by the electrons and are therefore protected from outside influences. Yi described the need for embedding the nuclei in crystals in order to eliminate the recoil momentum, as in the Mossbauer effect. He mentioned the fact that nuclear transitions generally involve energies on the order of hundreds of keVs or MeVs. Such high-energy transitions cannot be driven by a coherent laser beam. The speaker then discussed thorium-229, which has a metastable isomeric excited state that is only 8 to 10 EVs above the ground state. This excited state can be accessed by coherent lasers in the vacuum ultraviolet, or VUV, region of the spectrum. Yi then discussed the process for producing VUV laser light with high peak power and narrow spectral line width. He described the use of nonlinear optical materials to combine ultrafast lasers, giving very high peak power, with optical frequency combs, giving very narrow spectral lines. Yi discussed the calcium fluoride crystal doped with thorium-229 used to demonstrate the laser-driven nuclear transition in his lab. The initial results indicate the presence of 5 transitions, each with a half-life on the order of 700 seconds. These 5 transitions result from the electric quadrupole moment of the nucleus in the presence of an electric field gradient. Yi then described the way in which solid-state nuclear clocks could benefit other fields of physics, including the search for dark matter, the precise measurement of nuclear quadrupole moments, possible variations of fundamental constants, and the possibility of CP violation. He briefly discussed the use of thin films doped with thorium-229 for future research on nuclear clocks. The speaker concluded his talk by saying that the development of nuclear clocks constitutes a, quote, fusion of physics, bringing together precision laser metrology, nuclear and fundamental physics, ultra-fast science, and integrated photonics. The lecture was followed by a question and answer session. PSW member and Nobel laureate Bill Phillips asked about the use of nuclear clocks to measure changes in the fine structure constant, commenting that changes in the nuclear coupling constant would produce similar effects. He asked if nuclear clock measurements could be combined or compared with atomic clock measurements in order to distinguish the two effects. Yi responded that such side-by-side comparison experiments are being considered. Yi emphasized that signals from nuclear clocks might indicate changes in the fine structure constant, but certainly would not be considered conclusive. A member asked whether increasing the number of nuclei measured would reach a point of diminishing returns. In other words, at some point, does increasing the number of nuclei begin to increase the noise? Yi responded that we have not yet reached that point. He described statistical underscatter and overscatter, indicating that current research is entirely within the underscatter regime. He said that if the statistics can be improved to reach the overscatter regime, that would indicate either an uncontrolled experimental parameter or new physics. A member on the live stream asked what the biggest challenges are for exploiting the increased precision of nuclear clocks. Yi responded that laser technology is the biggest hurdle. He said that the development of high-power, narrow line-width lasers would greatly speed up experiments and serve to advance the field. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,505th meeting of the Society at 10:03 p.m. Eastern Time. Temperature in Washington, D.C., 6.7 degrees Celsius. Weather, cloudy. Audience in the Powell Auditorium, 63. Viewers on the live stream, 23, for a total of 86 live viewers. Views of the video in the first 2 weeks, 472. Respectfully submitted, Scott Matthews, Recording Secretary.
Well, thank you, Scott. Once again, an excellent job. Do we have any corrections, comments, additions on the minutes? Okay, I have 2. One is, I think you said the Bohr uncertainty principle. Is that correct? Because I always thought it was the Heisenberg uncertainty principle. Or did I hear you wrong?
No, that's what I said, and that's what I have written here.
Well, you might want to check that. The other point is he mentioned uranium as being a better material for a nuclear clock, but that it was beyond the reach of current technology. And you might want to maybe add something on that. But that was a stunningly good summary of his lecture, from which I caught a few things that I actually had not really gotten the first time around. Thank you. And so we now turn to tonight's lecture by JoAnne Hewett on the science driving particle physics and big accelerators. JoAnne is director of the Brookhaven National Laboratory and president of Brookhaven Science Associates, which manages the lab for the Department of Energy. In addition, she is professor in the Department of Physics and Astronomy and the C.N. Yang Institute for Theoretical Physics at Stony Brook University, and once known as the State University of New York at Stony Brook. Back in my day, JoAnne serves as chairperson of the DOE-NSF High Energy Physics Advisory Panel and was an ex officio member of the 2023 Particle Physics Project Prioritization Panel, fondly known as 2023 P5, about which we will hear something tonight. Her own research is on the fundamental nature of space, matter, and energy, in particular in theoretical physics beyond the standard model, and how to design experiments to explore its predictions. Among other honors and awards, JoAnne is a fellow of the AAAS and the American Physical Society, and she served as chair of the American Physical Society's Division of Particles and Fields. She earned a BS in Physics and Mathematics at Iowa State University, an MS in Physics at UC Irvine, and a PhD in Physics back at Iowa State University. And she spent a good deal of her career, almost 40 years, at 30, at Stanford University SLAC, the Stanford Linear Accelerator, something or other, which I forget, Center. As usual, all questions will be fielded in the Q&A session after the lecture. And so without further ado, JoAnne, the stage is yours.
Okay, thank you. It's an honor to be here tonight and give you a lecture at the 2506 meeting of the PSW Society. That is truly impressive, I have to say. So, as Larry said in the introduction, I'm going to tell you about the results of strategic planning process that was just taken a year ago here in the United States for the field of particle physics, which is known for its big, large accelerators. And I wanted to start off on this first slide with an event that happened at our own big, large particle accelerator at Brookhaven National Laboratory. We operate the relativistic heavy ion collider. This is a single event from gold collisions. So the collider, if I get this thing to work, hey, I did. Okay, so the interaction is right here. The beam, the gold ions are going in and out of the screen, if you like. And this is a 3-story size detector that is fully instrumented, completely surrounding the beam pipe, shaped in a cylindrical shape. So people always say it looks like a can of tomato paste, only 3 stories big. Each part of this detector is different types of instrumentation as you go from the collision all the way out to the end. And each of these colored tracks that you see are actual particles that are final states in the collision as they traverse the detector from the collision. And their energy and momentum and tracking is deposited in the detector as they move along. That's a lot of tracks. Can you imagine the poor person having to do all of the wiring to make sure everything's plugged in the right place? So anyway, this gives you a feel for the type of science that we do. And I'm going to start at the very beginning so that we all have the similar foundation and know a little bit about the language of particle physics. So our language is in quantum field theory. This is, I always like to say, this is quantum mechanics on steroids. It's actually a second quantization of quantum mechanics. And everything that we do in particle physics is done in this language. Dick Feynman, absolute genius, was a guy who made it simple for us to do calculations in this language. All interactions can be represented in a picture. Oh, this is kind of cool, actually. I like this thing. In a picture with this diagram here, this is an interaction between an electron that's traveling through space. Here it is, just trucking along in space, and it interacts with a photon, which is the quanta of light. Nice, simple picture to demonstrate what's going on. Dick Feynman gave us the rules, if you like, such that any enterprising theoretical physicist can sit down and calculate the rates of these interactions in any given situation. So we'll be seeing a lot of these types of diagrams as we go through the talk. And just keep in mind, we're just representing how particles are interacting. We have what's called the Standard Model of Particle Physics. This describes everything we know about the universe. Everything, except gravity. So this equation here, it's in quantum field theory. This describes every single interaction in the universe, except gravity, in 12 terms. When I mean everything, I mean everything. This is the very fundamental interactions of the very basic fundamental particles of which everything is made out of. And you can actually describe everything by these 12 terms. Never mind what the terms actually are. Just be in awe of the beauty of the simplicity that we can describe the universe in 12 terms. This chart over here on the left-hand side are the fundamental particles in the Standard Model. We have a lot of them. These are all point-like as far as we know, as far as we can determine experimentally. And they come in two main types. These particles, the purple guys and the green guys, are particles of which matter are made out of. And the red guys are force carriers. So these are the quanta that transmit forces between the matter particles. Why do we call these matter particles? Here we have quarks. The purple guys are quarks. The green guys are leptons. So up quarks and down quarks make up protons and neutrons. You put protons and neutrons together with electrons, and you've got atoms. So this is how you build up all of the atoms in the universe, as we all know from basic chemistry. It's just different numbers of electrons in their shells and different numbers of nuclei in the nucleus of the atoms. And it's all made out of up, down, and electrons, fundamental point-like particles measured at the level of 10 to the minus 18 meters. Okay, a size of a proton is a femtometer, or 10 to the minus 15. So the current limit on the size of these fundamental particles is 10 to the 18. What are these other guys? I wish we knew. We really don't know. We have found them experimentally. What are they good for? What do they do? We really don't know. I'll say more about them in a bit. But first, I want to talk about the force carriers. Those were the red guys in the previous chart. Now they're the blue guys here in this chart. And I just want to walk through the forces a bit. The first is gravity. As I said, gravity is not contained in that equation that we saw a couple of slides ago. That was the blueprint of the universe. And that's because gravity and quantum mechanics don't get along. It's mathematically inconsistent to embed gravitational interactions into a quantum theory. This is a whole field of theoretical physics called string theory. And we're not going to talk about that anymore tonight. It's to just say this is still an outstanding problem. Okay? So gravity is the one thing in the universe that's not contained in the Standard Model. It is the weakest of the four forces, My husband is very fond of telling me every time he trips that gravity is not actually that weak of a force, but it is the weakest of the four forces. So now let's go to the other three. Electromagnetism, this is something that we all know, we're very familiar with. Electricity and lightning, we all know how magnets work. That's electromagnetism. The quanta that carries electromagnetism is the photon up here, and it is massless. The third force is the weak nuclear force. The quanta which carries the weak force are the Z and the W bosons. These have masses. This is the force that's responsible for radioactivity, something of which we're aware of in our daily lives. It's also the force that's responsible for the fuel in the sun. It's what makes the sun burn, or the weak interactions as the nuclei fuse together. Hopefully someday we'll have nuclear fusion on Earth in a controlled way. And that will be the weak nuclear force that's responsible for that. And last but not least is the strongest force. This is the strong nuclear force. The quanta that mediates that are gluons, okay, here. This is what combines quarks inside of a proton or a neutron. Quarks are confined. They're not free. They're not roaming around in space like the whole rest of the particles can. They are inside of a proton and they are confined by the strong force. That's why the gluon is called a gluon. It's because it tends to glue the quarks together, sort of like a spring. If you try and pull them too far apart, they'll just spring back together. What actually happens inside of a proton, how this actually works, is described by a theory, but it's at such an energy that we don't really know theoretically how the theory works at this energy. Okay, so this is going to be a subject that we return to later in the talk. We need experimentally to determine how quarks and gluons behave inside of a proton to give the proton the properties that it has. That's a question that's still outstanding. We don't know. Okay, so now we know the particles and the forces. Here we go. This is the full standard model, our building blocks of matter. The particles are point-like. They're not constituents. They do not have constituents. They're point-like. The force carriers, these red guys, communicate the forces and the interactions between the matter particles. The purple guys, which are the quarks, and the green guys, which are the leptons. These interactions of the force carriers are based on mathematical symmetries. And we know them and we can calculate them very well within this language of quantum field theory. This structure is experimentally confirmed by every single experiment, okay, that we have done. So just to say a little bit more, while this structure is confirmed, there's some very puzzling aspects to this structure. So I told you, and I'm sorry, we switched it on you here. The quarks are now on the bottom and the leptons are now at the top. So sorry about that. A proton is made of up and down quarks. You put electrons with, and that becomes nuclei. You put an electron with that, that becomes an atom. You have the electron neutrino. That comes in through the weak interaction, so that's what causes radioactivity or the sun to burn. What are these other guys for? What do they do? Why do we have them? Outstanding question. We don't know. What's represented here by the size of these guys are their masses. So these are known as generations, first generation, second generation, third generation, because as you go across, they have the same properties, same quantum mechanical properties. They have the same electric charge. They have the same spin. They have the same color charge. They have the same weak charge, but their masses are different. So the size of these balls that I've drawn here are proportionally to the size of their masses. So look at the difference between the up quark and the top quark. The top quark is extremely heavy. It's 175 times the mass of the up quark, or actually the mass of the proton. Why? Why does this thing exist, and what does it do for us? That's something we'd like to know. So we look at the bosons. These are the guys that have integral spin. Spin is a quantum mechanical property, and so these are the force carriers. So as I alluded to before, the photon, the quanta of electricity and magnetism, and the gluon, the quanta of the strong nuclear force, they're massless. Okay? But yet the quanta of the weak nuclear force are massive. They're like 90 times the mass of the proton. They're actually reasonably massive. How does that come about? That comes about from a theory that was invented 60 years ago, which gives us the Higgs boson, which was discovered 12 years ago. So the Higgs boson is spin 0. This is a totally new thing. It's very much a part of the Standard Model. All of the interactions for the Higgs boson were in that first equation that I showed, the blueprint of the universe. So why were people thinking of a Higgs boson 60 years ago? Because this is before we even knew quarks existed. This is before we knew about W and Z bosons. It's before we knew about the Standard Model. They were thinking about it in terms of condensed matter physics in very related situations. So the explanation and what the Higgs boson does for us is it gives us mass. The Higgs boson gives mass to all of the massive particles. So that's the W and the Z bosons and all of the quarks and the charged leptons. It came about, Peter Higgs, hence the Higgs particle, was walking along in Scotland and was looking at the scenery, and the shape of the hills in Scotland reminded him of this potential that you see behind his shoulder here drawn on the blackboard. You can kind of see it, right? There's a valley and you've got hills on either side and a little hill in the middle. You've got the same type of shape here. This potential is what drives the Higgs mechanism. And there's a vacuum in this potential for which the universe sits in. Okay? These ideas breaks a symmetry because you're picking one particular point out of any point where the universe could sit in this Higgs potential. So you break a symmetry, you give masses to particles. That's the idea at the time. It requires a new particle called the Higgs boson, and Peter Higgs wasn't the only person thinking about this at the time. In fact, there's 4 original papers on the Higgs boson, all in the summer or fall of 1964. Higgs wasn't even first. Engler and Brout from Brussels were first. Higgs was second and third, and then you had Guralnick, Hagen, and Kibble coming in next. Why is it called the Higgs boson? Only one of the papers actually contained the particle. The rest were all very esoteric, very theoretical. This is how you might break symmetries. You have this funny shaped potential. Higgs was the only person that realized that this theory gave rise to a new particle and that this new particle was a spin 0 and was of a fundamentally different type than any other particles that we knew at that time. So the thing that you also might ask yourself was it original? Let's look at the dates. We've got June 64 with Engler and Brout, July 64 for Higgs, Higgs again in August of 64, and then these 3 guys were in October. They were definitely too late. But this was 1964. We didn't have the internet. Might not even had telephones in Scotland in 1964. I don't know. I know places in rural United States that didn't have telephones in 64, actually. And you think of the things that happened. It was 60 years ago. This is a long time ago. And 64 was actually a pretty amazing year because you had these very fundamental works in theoretical physics And in Bell Labs in New Jersey, McKenzie and Penzias discovered the cosmic microwave background. And then society was undergoing major, major changes with the Beatles and Nobel Peace Prize and the Civil Rights Act and free speech at Berkeley, the Ford Mustang, and Elizabeth Taylor and Richard Burton got married for the first time. So 64 was really an amazing year. In 1964, my main concern in life was whether or not my parents were going to take me to see Mary Poppins. So that's how Mary Poppins made the thing. And it was discovered in 2012. So ever since 64, particle physicists have been looking for this thing to see if the theory was right. So it took almost 50 years to find it. We'll talk about the collider in which it was found in a couple of slides. It was discovered in CERN, the Large Hadron Collider in Geneva, Switzerland. And it was discovered in a different way of interacting than you would expect. It was discovered in a decay mode. That's the different ways it can decay. That is its actual smallest decay mode, or one of its smallest decay modes. And that's the 2 photons. Now, for those of you who've been paying attention, you're going to say, but the Higgs doesn't have a charge, it's neutral. How can it couple to a photon, which couples to charge? Okay, here's where quantum effects come in. So here's our Feynman diagram. You have the Higgs. Oh, I clicked. I didn't mean to click. We're showing how I'll replay it. We're showing how the Higgs appeared in the data. Okay. The Higgs couples to 2 photons by this quantum loop. This is a virtual loop. These top quarks pop in and out of the vacuum. Remember, top quarks are really, really heavy. Higgs boson couples to mass, so it has a very large coupling or interaction rate with the top quarks, and then they couple with photons. So this is how a Higgs can decay to 2 photon pairs at a very, very small rate compared to other things, but in a final state that you can actually see at the collider. Remember that first picture I showed you with the event from a collider? Most of the decays of the Higgs boson, you can't indistinguish from that maze of blue and green tracks. But with 2 photons, you can. So that's how they found it. And we will look at it again. I think I have to go back, and then we go forward, and I click one more time, and we'll see the movie. So the Higgs is at 125 GeV, and here's the data as it comes in, and you just sort of watch this point. So the data is coming in, and there it is at 5 sigma. That's the discovery. That's a little blip. Okay, so this is where we were in 2012. Now, fast forward to 2024, this is like a huge peak. Okay, it's really, really distinctive. Okay, but this was the 5 sigma discovery. Higgs was still alive for his Nobel Prize. He shared it with Brout and Engler, only one of which was still alive. So Brout was no longer with us. So Engler and Higgs won the Nobel Prize. And there's a very sweet picture of Dr. Higgs when this was announced in the CERN auditorium, and he's crying. It's a very sweet picture. All right, so we have the Higgs boson. Now the standard model, oh, now we're seeing this again. Okay, now the standard model really, really is complete. We have everything. This Higgs was the last piece in the puzzle. We've been searching for it for 50 years. We have it all. So are we done? What do you think? Can we all go home? No. Around that same time, there are some very spectacular revelations from cosmology. So from astrophysical measurements that had been building up actually through a series of decades. You've probably had dark matter talks. If you haven't, you should have one that's focused right on dark matter, because this is the most pressing problem in front of particle physics today, in my view. And that's the content of the universe is very different from what we thought it was. So the atoms, our beloved, our precious standard model, is only 4.6 of the universe. us, stuff, this podium, everything, stars, galaxies, 4.6 of the universe. What's the rest of the universe made of? We wish we knew. We know that there's two different components, though, and we know that there are these two components from this suite of astrophysical measurements, okay? And it's basically gravitational measurements. It's only gravitational observations which show this. So 95% of the universe is unknown. Of that 95%, 71% roughly is this mysterious quantity called dark energy. Okay, a very mysterious sounding thing, which is responsible for the fact that the Earth is expansion is accelerating. We're not expanding at a constant rate, it's accelerating. So you think of blowing up a balloon. Normally you get tired when you're blowing up a balloon, but no, the universe is just going faster and faster. And then the other 24% is something called dark matter. This is known to be a particle. Have no idea. Does it interact with the standard model at all? We don't know. We've only observed it gravitationally. Why is it called dark? Because it doesn't interact with photons. It doesn't interact with light. So it's called dark. Okay. We'll come back to this. But this gives you the idea that as you get more and more answers to the questions you had, it opens up new questions. So I thought I would try this Google AI bot thing out because I usually ignore it. You do a Google search and it gives you this AI thing at the top and you go, I didn't want that. You just go through it. But I tried it with answers, open new questions, and it did pretty well. It means that when you receive an answer to a question, it often leads to further inquiries or new areas of exploration. And then it gave me an example. It must know I'm a scientist because it gave me a science example, and that's always kind of scary when you think Google knows something about you. So the question was, why is the sky blue? That's the original question. And you learn that the sky appears blue due to the scattering of sunlight by air molecules. But then you got all sorts of other questions in your mind, like how does that actually work? How do I calculate it? What is the process? Why does the sky change color at sunrise and sunset? So that is how you have a question, you answer it, and you have a whole list of other questions. Well, that's what we have. We have our standard model, but we have a whole list of questions that it doesn't explain. And they're really fundamental. So why are there so many kinds of particles? I already alluded to this second and third generation of fermions. Why we have them? We know there's 3. 10 years ago, we didn't know there were only 3. Was there a 4th generation? Was there a 5th generation? There was a lot of work. I did a lot of work on that. We know from the Large Hadron Collider there's only 3. So we answered that question, but now why are there 3? What is the nature of neutrinos? They're in the weak interactions, but we know very little about them. The Higgs is actually unstable. Okay, so what stabilizes it? What's dark matter? What's dark energy? What happens inside of a proton? Why is there more matter than antimatter in the universe? We have all of these questions, and they're really burning. And in order to answer them, we need more experiments because physics is an experimental science. So we have a strategic planning exercise in the United States. There's actually one in Europe as well. Europe is undergoing theirs now, this year and next year. We finished ours in the US last year. Actually, it was a year ago this week that it was announced. And it's a 10-year strategic plan. So I called it a decadal survey because that's something, the abstract, because that's something everybody recognizes. It's not the decadal survey of astrophysics, but it is a 10-year strategic plan for the United States. They identify the science drivers. What are the biggest pressing science questions that are in front of us? And those are given here in 3 different categories of deciphering the quantum realm. So that's basically neutrinos and the Higgs boson. Explore new paradigms in physics. So that's looking for new particles. and illuminate the hidden universe. So that's dark matter and dark energy. So they are all related to these questions here that are our basic fundamental questions. All right. So what is the strategic plan? What do they do? Physicists have a whole suite of ideas of new experiments that they would like to construct and build and do. That's what physicists do. We like to do experiments. But we can't afford to do all the experiments that we like to do. So what you really need to do is see how many you can fit into a budget to make as much progress in science as you possibly can. Okay? And so that's what this is. Here is the suite of experiments that they came up with that they would like to operate, construct, or do research and development on over the next 10 years. It's fit to a budget scenario, so it is literally the most bang for the buck. How can we address these pressing science questions as thoroughly as technology will currently let us? That's key, as technology will currently let us. What do you do? Okay, so here's the suite of experiments, and it's very important. So this is time here at the top. Here we are in 2024, and they're 10-year plan, so it goes out to 2034. And you really need many different pieces to this plan. The most important is that you need experiments that you've already built, but you need to operate. Okay, so these are the guys in green. Okay, so you can see here in 2024, we're operating this suite of experiments, and then other ones are going to turn on. You need to build new experiments so that tomorrow you can operate them and get the results. Okay, so these are the pink guys that come in. These are the guys that they're recommending to construct. And then you need to have new pink guys on queue in 2035 to start building. And so these are the orange guys. You're planning for the next decades. You're doing the research and development because you don't quite have the technology yet, but you know if you could do something, then you could really make progress in science. So that's what this plan does. The other thing that you want in this plan is you want to cover these science drivers as much as you can. You want to answer as many questions as you can. And you want a variety of scale in the experiments. You want some small experiments so graduate students can actually get their hands on experiments and do data analysis. And then we've got the huge colliders that are multi-billion dollars. So there's a whole scale of experiments here. And that's what's healthy. So for the rest of the talk, which, when did I start? Nobody knows. Okay. Like 8:20. Okay. That's good. All right. Because I don't want to go too late here tonight. I don't want to keep you here for too long. So the ones I'm going to talk about tonight are these blue stars, but don't worry, they tend to meld together. A lot of them meld together. Okay. But let's talk about the strategic plan a little bit in abstract, because there's two main features, two main pillars of these types of experiments. One is that you investigate the particles of the standard model to death, right? You measure every single piece of them that you can as precisely as you can to look for imprints of new physics. The other is that you're just out there blatantly searching for new physics. Okay, so the particles that we have in the standard model, that we have the technology today to investigate in detail, are neutrinos. So this involves a new domestic facility, and the Higgs boson. The Higgs boson is a collider thing. So near term, there's an upgrade to the Large Hadron Collider at CERN that discovered the Higgs, and then far term is a new offshore Higgs factory. By far term, I'm talking 2040s. Okay. For the new physics we know exists, that's dark matter and dark energy. And then searching for the unknown is upgrade again to the Large Hadron Collider. And then what I'm calling a far term is a very high energy collider, like a muon collider or a proton collider, or something that's like at 100 TeV. I mean, something that I won't be alive for. So now I want to just go through each of these, just a slide or two on each one. So neutrinos. Why neutrinos? Why study them in detail? It's because we actually know very, very little about them. They're so weakly interacting. We've never been able to amass enough of them in one place that we can really study them. In fact, we know more about the Higgs boson than we do about neutrinos. And we only discovered the Higgs boson 10 years ago. So here's a list of things we don't know about neutrinos. It's very basic, like what's their mass? Do they have CP violation? Are there more than 3? Blah, blah, blah. There's a whole list of things. How are we going to do it? Well, we're building the long baseline neutrino facility. We're about 1/3 to 50% finished with this now. What this does is at Fermilab, so this is one of the national laboratories that's outside of Chicago in Batavia, Illinois. We're going to create a neutrino beam. We're going to shoot it through the Midwest, okay? Sort of goes through Wisconsin and Minnesota and out to South Dakota, to a mine in South Dakota. You know, we don't want these states to pay taxes for the fact that we're beaming neutrinos through their ground or anything. They're going to hit a very large detector that is about a mile underground, 4,800 feet underground in the Homestake mine. The detector is called the Deep Underground Neutrino Experiment, or DUNE for short, and in its first stage, it's 2 × 10 kiloton vats of liquid argon. Okay. The second stage will be 2 more of these 2 10 kiloton detectors. So this is what the P5 report recommended, was that we finish completing this, and it's expected to be done around 2030, and then we start building the other 2 detectors, because you really have to have a very large detector to amass enough neutrino interactions to be able to study them. So this, and this is a picture. So far, they've excavated the cavern for the 2 detectors. It's enormous. This is only half of it. I've never been there, but I'm told if you turn around and look in the other direction, it looks exactly the same. Okay, so it's just absolutely amazing what they've been able to do. And the science goals, so look at the mass hierarchy of neutrinos. Is the electron neutrino the lightest, the heaviest, the middle guy? We don't know. And to observe CP violation in neutrino interactions. Because we're going to have these very large vats of liquid argon, we can also look for proton decay. Used to be in vogue, but you know, it's still interesting. And you can use it as a neutrino telescope to learn more about supernova. If one were to go off nearby, but not too close, while this detector is in operation, you can measure the neutrino spectrum as they come off of the supernova and come through this detector. It's absolutely fascinating. Okay, so this is cool. This is the flagship facility in the United States. This is a $3 billion thing. Okay. Dark matter. So, to my mind, this was the most pressing problem in particle physics. The motto here is delve deep, search wide. Why? Because every single point in this parameter space, there's a theory to go along with it. Us theorists are very clever. We can come up with dark matter models till the cows come home. We love doing this. It's a lot of fun. There's some models that are more theoretically motivated than others, but basically it's a 36 order of magnitude mass spectrum that we need to explore. So this is mass, and this is interaction strength with the standard model. If it even interacts with the standard model, we don't know. Okay. But this is where the fun part comes in, because there's some big experiments I'll talk about one in a minute, but there's also a lot of small $20 million experiments with new technology, in particular quantum technology. Quantum sensors are really important for probing this parameter space here. So the gray regions in this plot are parameter regions that we've already explored. With quantum technology, we can basically explore a region over here that's about this big. Okay? So this is a case where new technological developments can come in and completely change how we do science. The big experiment, which was in the P5 report, is a continuation of a technology which gives us this particular excluded region here, this gray area that sort of looks like a hockey stick, and it's looking for something called WIMPs. WIMPs are weakly interacting massive particles. This is under the assumption that dark matter interacts weakly with the standard model. And what you do is you build a big tank of liquid xenon, in this particular case, that happens to be a very good element for this. You have to shield it underground, okay, mile underground again. And we've built a dizzying number of these types of detectors. And here's kind of where we are today. This is an interaction rate versus mass of this WIMP. Okay, here's we are today, which is kind of like here in this plot. We have an irreducible background from the sun. So at some point, solar neutrinos are a huge background to WIMPs, even if you're a mile underground. And we can only be above this irreducible background if we're above the blue region. So the goal is to build a big enough experiment that you reach this blue region, and then we will have searched as far as we can go. So this is 80 to 100 tons, not kilotons, but tons of liquid xenon. Don't know where it's going to be hosted yet. This is an international collaboration between the US and Europe. It can be hosted in Italy, in the UK, or the USA. Those are the contenders right now. And P5 would like it to, the strategic planning panel would like it to construct in late 2020s. So that's dark matter. Dark energy, we have an experiment from the 2014 P5 panel that's turning on next year. Very exciting. Yay, something that's turning on. Okay, so this is the Rubin Observatory, and it's going to perform a 10-year survey of the sky. It's in the Atacama Desert in Chile. So it takes photographs of the southern sky. There's a 3.2 gigapixel camera that was built by Slack, which is I manage the construction of that. I'm very proud that the camera is there safely on top of the mountain and being mounted on the telescope. So very proud of that. And it will observe dark energy by the observation of galaxies. So there's many different techniques by which it can observe galaxies and the motion of galaxies. And it also will observe out almost to the edge of the universe. So you'll be completely redshifted out in time, meaning that you'll be able to observe the dynamical nature of dark energy. Is it always at the same level as it is now? That's a question they'll be able to answer. They answer that by literally taking pictures of the sky over a 10-year frame. The camera shoots and points at a 3 square degree area of the sky every 15 seconds for 10 years. A lot of data. So anyway, that'll be very exciting. First light is next year. In a few years, you're going to have talk on this from hear the results. All right. Last but not least are the collider accelerators. Accelerators are powerful microscopes because you have very high energy particle beams that allows us to probe very small distances. So energy is related to distance inversely. Okay, so if you have a lower energy beam, this is what a particle may look like. However, if it has constituents and you have a higher energy beam, you can tell the constituents are inside of this. So that's the value of these high energy beams. You collide the particles together, you create this big field of energy, and it really goes back in time to the very early stages of the universe. Here's the history of the universe on one slide. We have the Big Bang. Bang. Here you have the inflationary period. Here we are today, okay, with our atoms. Accelerators bring us back to about 10 to the minus 10 seconds after the Big Bang. Here's where we are today with accelerator technology. Okay, so this is why we're able to create these new particles that really only existed during this time frame of the universe. Okay, we have 2 operating colliders worldwide today. The Large Hadron Collider at CERN in Geneva, Switzerland, and the Relativistic Heavy Ion Collider at Brookhaven National Laboratory in Long Island. So the LHC studies Higgs bosons in the standard model. It's really just a high-energy physics collider. RIC studies the quark-gluon plasma, which is the state in the early universe where you actually do have free quarks and gluons. We're able to recreate that in the accelerator. I'm going to speak just a little bit on the LHC and then come back to an upgrade to RIC at the end. So the LHC by the numbers, it's 17 miles in circumference, 300 feet underground, proton-on-proton collisions, 1,600 superconducting magnets that operate at 2 degrees Kelvin, so colder than outer space. 10,000 megajoules stored energy in the beams, 600 million collisions per second. Think of the data. And the LHC beams at their design energy of 70 eV have the same kinetic energy as an aircraft carrier at 15 knots. So when you have a beam dump, you have to do it very, very carefully. Okay. This is the largest scientific project ever completed. It's famous. I sit next to people on airplanes. They know about the CERN. They know about the Higgs boson. They know about the LHC. It amazes me. So this is the Higgs at the LHC. I showed you the plot that showed the discovery into this teeny tiny mode into 2 photons. These are all the different ways you produce the Higgs at a proton-proton machine, all the different Feynman diagrams that produce a Higgs, and all the different ways that it decays. So there's a zillion different final states you can look for to study the Higgs, and we've only started to scratch the surface. So currently, the interactions of the Higgs boson with standard model particles are measured at the 10 to 20% level. We need to measure them more precisely to know if the Higgs really is the Higgs the way we think it is, or if it's something else. So there's an upgrade to the LHC. So this is kind of a cheaper thing. It's only maybe $2 billion, to be honest. Worldwide, okay, United States is contributing to this. We're going to upgrade the luminosity, not the energy, but the luminosity by a factor of 5 to 7. So now instead of 600 million collisions per second, we're going to have 3 trillion collisions per second. This poses detector and computing challenges, so there's a lot of work for the physicists and the software folks to do. It's underway, it's ballistic, it's going. It will start operations by the end of this decade, around 2029, and will operate till the early 2040s. Right now they're saying 2041, which is amazing. And it will measure the Higgs interactions from 2 to 4% level. Remember, we're 10 to 20 today, and so this will improve it from 2 to 4%. So we'll really have the opportunity for new discoveries. But what we really want is a Higgs factory. So this is the far-term machine. And we want this to be an electron-positron collider. Why? Because electrons are fundamental particles. Protons are not. So the collisions are cleaner. Okay. Small backgrounds, easy to pick a Higgs out of this type of picture. I actually have a photograph of the Higgs here. Okay, try picking this out. Okay, so this is the LHC. This is the LHC upgrade on steroids. If we had this electron-positron collider, it'd be very easy to make ultra-precise measurements of the Higgs boson couplings. And for the past, 10, 15 years, we've been drawing these plots, which are dizzying. There's all sorts of different types of these Higgs factories proposed. They're the lines of these different colors. The point is, this is 1% measurements of Higgs couplings to different particles, and you see you can get to 1% or below, okay, if you had one of these machines. This is the level you need to see the quantum effects of new physics. So we really want this. There's two types of machines, two contenders, one linear, one circular. This has also been an argument for about 20 years. The linear colliders can reach a higher energy. It's easy to polarize the beam in a particular state, so you could reduce backgrounds even more. There's low radiation and energy efficient. Japan has expressed interest to host this machine. Circular colliders, beams circulate after collisions. You have the highest luminosity. You can reuse the beams over and over again, keep colliding them. Your energy is limited to about 400 GeV, and it's less energy efficient. Okay, so this linear collider is 14 kilometers long. Okay, you have an electron and a positron on each end and they collide in the center, 14 kilometers long. This is 91 kilometers in circumference. And CERN and China have expressed interest to host. So you will notice which country has not expressed interest to host. That is not part of the P5 plan. What is part of the P5 plan is that the US would happily contribute in this endeavor hosted somewhere else. It's because they're expensive, tens of billions of dollars. Okay, the US isn't going to do that. Give them $1 billion to do it somewhere else, fine. And we're starting to think about environmental impact of these machines as well, sustainability and all of that. And no matter what a person's politics is, and if you believe in sustainability or not, everybody believes in operation cost in the machine and saving on your electric bill. Okay, and so you want these colliders to use as little electricity as possible. And some of them, this is literally the list of designs. It's dizzying. Some of them are better than others. The light colored ones are better than the darker colored ones. The CERN one is actually particularly bad. This is my very last thing, is the electron ion collider. This is the collider that we're building at Brookhaven now. We're $500 million in. This is the only new collider to be built worldwide this decade. So currently we have an ion-ion collider. This is now going to collide electrons with ions. So it's like we're using this electron beam as a scalpel to probe and see what happens inside of a proton. Construction is underway. It's cheaper than most colliders because we're reusing the tunnel we already have. For the ion ring here, for this collider, we're using the ring that we already have. So it's like all we need to do is build the electron ring inside of the tunnel we already have. This has caught a lot of attention worldwide. There's 1,600 international collaborators, 80 US universities, 8 national laboratories. Looking at the international collaborators, it's about 30 from Asia, 30% from Asia, 30% from the US, and 30% from Europe. So it's really evenly distributed around the world. They're going to contribute to the construction and the cost of this thing. And operations should start in the early 2030s. We're terribly excited about this because it's going to answer one of those questions of what happens inside of a proton. Okay. All right. So that's it. We have a plan. We have a strategic plan. And it takes a very broad suite of different types of experiments, different times, different sizes, different costs to probe and unlock these secrets of the universe. And they have to be well planned because there's a lot of resources involved.
All right, well, we have time for some questions. Just please stand up and tell us your name and if you're a member.
Mike Albro, experimental particle physicist. A double question for you, JoAnne. So the electron ion collider, is there any interest in CERN collaborating with experiments there, and the
Yes.
other way around, a Brookhaven physicist collaborating on CERN experiments?
Absolutely. So Brookhaven, so there's two main experiments or detectors at the Large Hadron Collider. It's called ATLAS and CMS, are the two detectors. And Brookhaven is the U.S. host lab for all U.S. participation in the ATLAS detector. So we already go in that direction, no question. And we're already starting to get involved in their big circular machine too, if they actually get to build it. For the electron ion collider, yes, I actually am going to get them to contribute to it. In fact, they're literally just signed the paperwork this week. They're going to do some R&D and some sensors for us. Yeah.
Blue microphone, stand up, tell us your name and if you're a member.
James Cole, member of the Society. I noticed you talked about electron-positron colliders, but what about muon colliders? Because they would have lower radiation losses, and I'm wondering why you haven't mentioned them. Thank you.
I didn't mention them because they're so far out in time that I didn't know what to do. I thought I was talking a lot already anyway. But they're on this, if I can get back here relatively quickly, they're on here. They are this thing called, where is it here? Oh God, where are they? No, it's not MUDI, it's the multi-TeV. So they're second from the bottom. They're out here. They're part of this. They're way far out. Maybe we could start construction 2040s late, maybe 2050s. There's a lot of technology issues with them that we need to solve before we can build a muon collider. But people are really excited about it because physicists like technical challenges, and so they're really excited to go do it.
Red microphone.
Yeah, you can go back.
My name is Mike Helton. I'm a member. My question is your opinion about the characteristics of these small particles that make up neutrons and protons. And so we all know that the combination of those particles with electrons make up the periodic table, and thus we have the universe as we know it. But if the characteristics of these small particles change a little bit one way or the other, and the nature of them are a little different, is it possible to have another kind of universe and maybe even support a different kind of life?
I am never one to say that anything is impossible. I'm a theorist, right? So I believe all things could be true. But I would say that if you change the properties, you wouldn't have the universe that we have now. The universe that we have now is very, very dependent on these properties. For example, the strength of the interaction that I showed at the very beginning between a photon and an electron, if that were to change just by a bit, atoms wouldn't form.
Blue microphone.
Colin Alberts, I'm a member. I have a question. Okay, I have a question regarding your comments about strategically picking how to allocate these resources. Has any thought been given to dusting off any of the mothballed hardware and material for the superconducting super collider? Because as I understand it, the tunnel is dug and there's plenty of material there. It's sunk costs that you might be able to get something out of. Has that been thought of?
Unfortunately, so much time has passed. It's 30 years, right? It's really not possible. A quarter of the tunnel was dug, as you said, and it's collapsed.
Oh,
So you'd have to redo the tunnel. The magnet work has continued. Okay. Magnet work has continued, and this large circular collider, future circular collider, as CERN is talking about, the continuation of that magnet work might be used for putting hadrons, protons, into the ring in the 2070s.
nothing else can be salvaged from it?
But no,
Oh.
it's just gone.
Okay.
Red microphone.
Hello, my name is Srinivas Ayagari. I'm not a member. Speaking as a layperson who reads about this, and you talked extensively about how dark matter and dark energy are the most pressing problem in particle physics. you sense in, reading from a layperson's perspective and the kind of, articles that are directed more toward lay people who are interested in science, that there might be some impatience with the idea of dark matter as it is, and people are coming up with different kinds of theories that may explain our current universe without a dark matter or dark energy. What do you think? Is there any credence to those? You seem confident in the particle theory of it, but I just wanted to know from your perspective.
I have not yet seen a paper that was plausible all the way through from start to finish. Let me just put it that way. I have not yet seen a paper that was inconsistent, or excuse me, was consistent with all of the observations we have to date.
Blue microphone.
Eric Enig, I'm a member of the society. So I've heard a lot about electrons and standard model. I look around, I see composite particles are underrepresented. So I represent the ion. We do work with, we've borrowed from the racetrack microtron structure. And rather than injecting electrons to accelerate, we're actually injecting ions for the purpose of aggregating charge. Mm-hmm. And so our application is for RF generation in a very small structure, RF in the 3 to 300 kilohertz. So this is very large wavelength from a very small structure. But there may be other applications. So how do we, as a small business, get in front of researchers at Brookhaven to discuss this technology?
Shoot me an email.
Okay, thank you.
We have several dozen people watching online. This person has a few questions. This is Siobhan Rao from Melbourne, Australia. And the question is, in the decadal plan, is there an experiment being designed to explore the mechanism that gives neutrinos mass?
Yes. Well, I'm going to say yes and no, because this plan was for the high energy physics part of the Department of Energy, and it's nuclear physics part of the Department of Energy that has the experiment that's going to do an absolute measurement of the neutrino mass scale. They came out with the long range plan at literally exactly the same time, and that experiment is in that plan. So there is an experiment, just not this particular plan, another plan.
Thank you. And two more follow-on questions from the same person viewing online. Has supersymmetry been ruled out at the TeV scale, as no promising results have come out from the Large Hadron Collider? And then also, why is gravity such a weak force compared to others? Are there any experiments planned to resolve this?
Okay, so no experiments yet planned on the second part with respect to gravity. Got to come up with some good ideas that are technically possible. For supersymmetry, this is actually a complicated question. I spent many years of my research life looking at this question, trying to think of ways supersymmetry could hide at the LHC. There actually are plenty of ways supersymmetry could hide at the LHC, to be perfectly honest. It doesn't take a lot of theoretical thought to weasel around some of these things. But most of the mainstream supersymmetric theories have not yet been found at the LHC. It doesn't mean that supersymmetry is excluded at the TeV scale. It doesn't mean that it's excluded, period. It could just be heavier at a higher scale.
And we have one more question from Eric, who's tuning in from Sweden. Eric says, how about LISA looking for gravitational waves? Is that part of this? And LISA is the laser interferometer space antenna.
Yeah, really, really important. LISA and upgrades to LIGO, they want to do something called the Cosmic Explorer. Really, really, really exciting experiments. Not part of this because you guys are going to laugh at this. That's funded by the NSF. And I neglected to mention this is a Department of Energy plan. And so no, it's not part of this plan, but I know the NSF is moving forward with gravitational waves and are looking at it independently. And it's even a different, it's not the high energy or the EPP part of NSF. It's a different part of NSF. Yeah, So not part of this plan, but still under consideration through another plan. Each area has its own plan.
We're going to go to the red microphone, but before I forget, I want to mention that PSW's had a talk on the Rubin telescope, which at the time was called the Large Synaptic Survey Telescope,
right,
by Stephen Kahn. back in 2016. But if you want to know what the plan was, you can watch that talk. And we also had a talk by Nigel Lockyer, who was at the time in charge of the experiment for the neutrinos from Fermilab.
Yeah.
And you can hear him talk about that experiment and what that plan was also on PSW Talk. So with that, the red microphone.
Yes, I'm Federica Darima, a member. Thank you very much for this very end-to-end kind of presentation. I have two kind of twofold questions. First of all, and you alluded to that at the end, we are looking, in addition to all the accelerators projects, we are looking also into astrophysics. So how measurements of those can help prioritize some of these measurements? You have like a 30 kind of projects. And if somebody was asking, which would be the top 10 to start with? I know you had some timelines, but still there was a long list.
The timeline was actually very carefully considered. The first consideration is that we want to finish the projects we're already constructing. Okay. And then because we're fitting this into a budget, how much money gets freed up and what coming in costs the most. And technically, when are things ready? Okay. So this offshore Higgs factory, if it's the circular collider, not the linear version, technically it's not ready yet. The linear version's ready, but the circular one is technically not ready yet. So that pushes that out. Okay. So it's technical readiness and budgetary and finishing up the stuff that you're already doing.
So I had a question on funding for the linear collider and why the U.S. is not interested in citing it here. It's just political and money.
Yeah, it's money.
And there's no way to leverage SLAC's linear.
It's too short.
Infrastructure.
It's too short. Too short. And it's also next to the San Andreas Fault. So you probably don't want to spend $20 billion on something that is right next to the San Andreas Fault that literally just had an earthquake yesterday.
You mean San Francisco?
Just saying.
San Francisco made a big mistake then.
Yeah. There actually was a site way back when, probably 30 years ago, well, 25 years ago now, in Central California, near Tesla, which is interesting. There's a town called Tesla, California, and it was a site near there. But it's just money. There's no political will in the U.S. to do it. I don't think there's a lot of political will in Japan either, unfortunately.
Blue microphone.
I'm Bob Hershey. I'm a member. If all goes well, what will be the next thing that we hear where something has been a success according to your plan?
Rubin Observatory. Okay. It was really kind of the last plan from 2014, but nonetheless, finishing that up is still in the plan. The next thing will be the upgrade to the Large Hadron Collider. So you'll hear about that. And then when the neutrino facility comes online at Fermilab, that'll be a big splash in the U.S. So those are the first three things.
In the construction of that facility, is it the work at the mine that's the hang-up, or is
it was
technology work at Fermilab that has to be
no,
done?
It was really there are a lot of people that learned more about excavation of caverns a mile underground than we ever knew before. Yeah, but that part is done. So that was the riskiest part of the project, and that part is done. So now it's just physicists doing their thing, but every single piece of equipment that they build goes down a small shaft a mile underground, so it goes slow.
Any other questions? All right, no more questions. Then before you go, we have a few gifts. One is a framed copy of the announcement of your talk, signed by all members of the General Committee on behalf of all members of PSW. Another is volume 1 of the Bulletin of the Philosophical Society of Washington, in which you can read who founded the organization, why they founded it, why they called it what it is, and a nice description of how scientific discourse should be conducted, apolitically, mind you. And then finally, we have a ribbon for you, which on its side has 3 stripes, evoking the symbol for inductance, named for our founder, Joseph Henry. And as you pointed out,
He has a
he
unit.
actually has a unit named for him.
Unit.
And someday we're going to have a story about how it came about that the unit is named for Henry. And with that, we thank you so much.
Okay, thank you
for a
very
wonderful
much.
talk.
Thank you.
Lest you worry, the actual objects are here in the back of the room. They're not just virtual pictures. And now for my embarrassment, which is I'm not sure what we're going to do on the 20th, but if we do have a talk, it'll be the 2507th meeting. And I have people who are supposed to commit to these other dates, but right now all that's scheduled is Nick Lane, professor of evolutionary biology at UC London, who will be coming from London to speak on his theories of the origin of life on February 7th. And then we are supposed to have a mini JWST conference on Saturday, February 22nd. And then on March 7th, Joanna Drucker will be coming to us from UCLA to talk to us about the origin and development of alphabets. We will post information to the website as soon as possible. Let's thank our crew for helping out tonight and running our video. And with that, I will accept a motion to adjourn the 2506th meeting. Do I have a second? All members in favor of adjourning to the social hour? All members opposed? The lecture portion of the meeting is adjourned to the social hour.